So I picked up a topic of OHM Sponge as a way to just give you some idea about how and what we do at Northwestern. So I picked up the corny title as Hip, Hope, or Full of Hype. I'll give you the answers already. I'll tell you that it's definitely full of hope and hip, and it's not a hype. And let's see how we go from here. So what I want to do is give this example of the sponge concept that we have developed for environmental remediation, and then show how this type of work also requires the facilities and instrumentation. So whether it's oil spill or environmental pollution, these are massive problems, right? Gigaton problem, as we often say. But remarkably, there's a potential for a nanoscale solution to this gigaton problem. And then that is the essence of what I'd like to present today, to give you a sense that some of the most complex problems, such as environmental remediation, has the basis for molecular level understanding of materials and interfaces. And hopefully that'll give you the appreciation for hierarchy of length scale, going from molecular scale to environmental length scale, how some of the capabilities that we have come to fruition. This is a part of our comprehensive strategy in our group only in recent years, where we want to use this multifunctional nanostructures for some of the problems with the environment. It's one of those things doing well and doing good. It's a major innovation of one of my senior group members, Vikas, and there's a startup company, etc. If those of you are interested, we'll be happy to describe. But I wanted to take a step back and give you a sense as to why and how some of these issues have become so germane in recent times. If you look at growth and progress of any society, they sort of ride on these three-legged stool, I often say. Energy, so not just the supply side of energy, but the storage and the distribution. So one of my very good friends who was the founding member of ARPA-E, which is the DARPA version for energy, and he often said that if Thomas Edison were to just pop up in today's world, he would not be surprised to see how electricity distribution is. It's effectively the same one that he used 120, 30 years ago. So that's something I think we need to worry about in the future, is to improve our smart grid and all the other things that you must have heard about. Secondly, sustainability of materials, processes, systems, and of course, environment is something we are surrounded with and immersed in. So a balance of these three things is absolutely critical. And the point I'm making, as you might have seen yesterday, the ex-Vice President Biden has come up with this global climate change strategy for renewable energy at $2 trillion, which addresses many of these issues. But the point I make is, whether it's energy, sustainability, environment, beyond just feeling good, you need to propose a value proposition as to what is it for the society as a whole. And that is the consideration which is almost always lost. It tends to be only one or the other. So all three issues need to be taken into account. And I show this slide to emphasize, until probably Obama years, there was no strategy in America. It was more like a miracle. And obviously over the last 10 years, a lot of things have happened, many of them positive. But nevertheless, there's been a tremendous emphasis on fossil fuel, as you know, at least in the last century. So 10 years it is reducing, but this issue of transport of fossil fuel almost always leads to spilling and pollution. And I enjoy showing this slide because this really covers all of the oil and gas companies in the context of the wars that we had. You can see we shall not exonerate Saddam, and all these are oil companies. So there's a lot of interest in the Middle East, largely through oil. So you can imagine if we start to have renewable sources, then our dependency in the Middle East is going to wane away. It already has waned away. So the last 10 years have been amazing in the energy scene. But this is something that's going to stick with us for a very long time, because oil and gas are being used and will continue to be used in some capacity for foreseeable future. You'll notice that there was a big spill in the river in Russia a few weeks ago, and that river joins Arctic. And now you can imagine with the summer going on, Arctic is melting. So there's a tremendous concern that a lot of this oil is going to move into Arctic Ocean, and this is going to really compromise health, aquatic ecosystem, fishing. When I first came to America in late 80s was the first time I heard of Exxon Valdez. Some of you may remember there's a huge spill tens of millions of gallons in Alaskan Bay. So this oil transport and the spill has become a ubiquitous, and I have a series of cartoons, funnies like this, which are really not funny actually, they're so profound. Because BP might pay the locals to get compensated, but how about the birds and flora, fauna is completely destroyed. So we have a solution, and that's part of what I present today's first few minutes. Is called OHM Sponge. And the bottom you can see what OHM stands for. So oleophilic, it loves oil. Hydrophobic is it hates water, and that's what you need. You want only oil to be absorbed, not water, and that's why this is particularly interesting. And the third attribute of this material is called magnetic, and that's why it's called OHM or Om. If some of you may know the Sanskrit word, it means all eternal. So OHM is a new innovation in our group. And what this picture shows is on the left-hand side is water droplets. So it is so hydrophobic that it doesn't like to wet the surface. So you can see it bolts up. On the other hand, if we had oil droplet, they immediately get absorbed. So you can see there's no residue here. And our OHM sponge, we feel, has these 4 attributes. Economic, I don't want to spend too much time on this part because you're here for science. But economics is equally important sometimes because how science gets done is driven by economics, as you can imagine. It's very efficient because it absorbs oil. It's eco-friendly because the material that we make is all green chemistry, water-based, and is obviously, we think, is very effective. Part of the reason this happened is this collection of capabilities in the last 20 years. That's nanotechnology. You can see tools, make materials, compute, understanding of biology. And also the nanoscale really is unique in the following way, that it gives very unusual properties and phenomena. And the one among many that you see here that relevance to OHM sponge is the bottom left. We now have the ability to control surfaces with single molecule, and that changes the property and behavior of the material, which is pretty dramatic. So if you look at all the current problems, oil spill, first of all, it might be surprising to you that there's a spill every day that happens. There may not be the 10,000 or million gallon spill that makes up evening news, but virtually every day there is spill a few tens of thousands of gallons everywhere in the world. And these are the major remedies. One is dispersion. You basically disperse the pollution much broadly. So obviously you don't get rid of it. It actually is even worse in some cases. Booms and screamers are very low yield, so it takes forever to absorb and get rid of the oil. Burning is another legitimate approach, by the way, which is terrible because you're creating CO2 and obviously the whole region is going to get contaminated. And it's not just the oil that you need to remove. Comes with oil is mercury, cadmium, and other toxins which are dissolved. And that's I'll show you that OHM sponge even removes that. But last but not the least is sorbent. It's like diaper. Diapers are great to absorb fluid, but can you imagine reusing diaper? Not a great idea. It doesn't sound very appetizing to me. So what happens to diaper? They become landfill. So this is a real major challenge. And look, okay, even if you use fuel for transport, something else like batteries, there's so much petrochemicals in our society that there's no way oil is going to disappear suddenly if we decide to, because there's a tremendous value chain and supply chain that's integrated throughout societies in the entire world. So there are a lot of challenges. I don't want to spend too much time, including, there are these beautiful baby drill seafood surprises that we've been doing in Gulf and coast of Santa Barbara. So this is a solution. As I'll show you a short video. I think it'll be fun, and then we'll switch over the gear to facilities. So this is a short video. As you can see, this is OHM, oleophilic, hydrophobic, magnetic. We start with cheap sponge. You get your gift in December, say iPhone. You get this tiny iPhone, but there's a big box, and most of the box is sponge, and that you typically throw it away. So what we do is we take whatever discarded polyurethane, polypropylene, pick up rubber sponge, whatever. All we do is dip coat it, with few percentage of the slurry to make the sponge. So what you do is literally you take the polyurethane sponge and dip it in the slurry, squeeze it so it's all the excess fluid comes out. You dry it, and then you have an OHM sponge. Very simple. So what does it do? As you can see, If you put water droplet, most of the oil rather, and you can see the oil gets absorbed by the OHM sponge almost 20 times its own weight. If you look at regular sponge versus OHM, regular sponge absorbs water, OHM is bone dry, which is good. So that means you're removing only oil. We've colored oil red, so it's very easy for you to see, and look what happens. And so you obviously can absorb, and then you can squeeze and get the, oops, excuse me. Okay, there you are. And so this reminds me a very quick short segue. When I first came to America, I remember at late night, I used to watch television. This infomercial were very captivating, Kathleen. So they say, if you order now, you're going to get this, So, okay, so this is what I'm telling you. If you order now, you can remove oil from a sponge, squeeze it, but wait. If you do it in the next 24 hours, you can squeeze it and do it again. How many times can you do that? It turns out we can do that 20, 30 times. So that's pretty good. So as you can see, you can keep on doing that. And if, sorry. Okay, let's do it again just to make the point. So this clearly has some unusual property whereby it absorbs oil, and this is chloroform that's below the water, and you can see it absorbs chloroform below the water, and it's magnetic, so it can be moved around. So how useful is it? So let's look at a couple of quick slides, and then I'll explain the science behind it. Oops. So the question naturally arises, okay, what else can this sponge do? And so you can see at the top left, different types of oils can be absorbed at the level of 20 or 20, 30 times its own weight. So it's a very, very effective and very high efficiency approach. Top right, you see different pHs. Sometimes, different pHs can, behave differently. But as you can see, highly acidic to highly basic, you're getting same performance. And the bottom left, as you can see, number of cycles you squeeze. It's like household sponge, correct? You use it for water. If there's a spill of coffee, tea, you use it, squeeze it, you can do it many, many times, and it's still very effective. And a lot of the spills happen in seawater, oceans, where the salinity is 0.5, 0.6. But you can see up to even 1 salinity, the OHM sponge works very well. Just one last slide, just to hone in the point that commercial crudes are very complex fluids, correct? That's very smelly, by the way. I would not recommend. So the whole lab had to be shut down for a few days till the smell went. As you can see, 20, 30 times its own weight, we can do crude oil. So it's a very selective approach to absorb oil. And so I want to not go into more technical details of this, but to now switch over to a topic as to why this happens. So just bear with me for a few seconds and I will explain the. Okay. So can you see the slide, Kathleen? So it's called smart sponges. So what I just showed you is only oil spill, but as I'll show you that when you tailor the nanostructures, so you can tailor them to specific purpose. So it's almost like a OHM sponge, like a Swiss Army knife. It has multiple functionalities. So one I just described to you is oil recovery. But you can also, as I'll show you, you can oil spill almost always associated with mercury contamination, lead, because those are minority component in oil. So oil may come out and you remove it, but the dissolved lead and cadmium and arsenic and sulfur remains. So there's a need to remove that also. In some cases, as in the case of there's a lot of fracking that has happened over the last decade or two. And what happens is the fracking, this tremendous amount of water is used, and many of these, the water has oil contamination. So it's a majority water, minority oil, unlike the oil spill. And third is there are many places where fertilizer runoff goes through rivers and waterways and ends up in lakes and rivers, and they create this huge algae bloom that you see. So we have now developed this OHM sponge for all of these purposes. So you start with the commercial sponge, coat it with a nanotech coating, and then whether it's a soil, air, water, those pollutants get absorbed, you recover them, remove the pollutant and reuse. And so it's a circular materials economy, we would like to believe. So why and how does this happen? So this is where a lot of science has to happen. So this is a short cartoon, which is just to hone in the point that you can tailor the surface of this nanoparticle that some of the students are doing. So they can be affinity for specific purpose, like nutrients or like heavy metal or hydrocarbon groups. And you can do that with combination of composition and structure. And you can make this in the form of membrane, such as conventional cellulose, polyurethane, and these are magnetic membranes. If you look at the length scale hierarchy, you start with a large scale sponge. If you look at the micro scale, you can see high porosity, and you see these bright dots. Those are magnetic nanoparticles, which are slightly heavier elements, so they light up like Christmas tree. There's a higher magnification that you can see the ligaments of the sponge, and coating is on the surfaces. You can see that coating. This is in a transmission electron microscope where you can see ensemble of some particles, graphitic fringes that you see. And so the point I'm shifting is the functionality of OHM sponge. We are trying to establish what we often call form-function relationship or structure-property relationship, right? And the structure is in the context of structure across multiple length scale. It's not just a physical structure, how it looks like, but along all of the length scale, how things look like at the millimeter scale that you see at the top left, how things look at the micrometer scale, that's the scanning electron microscope type of length scale. How it looks at the nanometer or atomic scale is the transmission electron microscopy, and that's the sort of the capability that we have listed at the bottom. So what I want to do now is to show how these capabilities are brought to bear, not just for me and my student, but all of the students at Northwestern, the users who may need to use these capabilities. So with that, while I take a pause and take any question on OHM Sponge, I'm going to shift gear to our centers and facilities and show how the innovation that you've just seen, such as OHM Sponge, there are many other innovations at Northwestern. In order to probe as to why and how they work, we often make use of capabilities which I'm about to describe. But before I do that, I thought I'll take a pause and see if there are any questions, Kathleen.
Okay.
I hear that the students are extremely inquisitive, and so I was alarmed. I was asked that I should say that one at a time. I don't want all of them to ask questions all the time. So just one at a time would be perfect, if you could.
Kasim.
Hi. Hi, Dr. Dravid. I was wondering, I had two questions actually. One, once you absorb this oil, do you have a plan for where you might dispose of it? Or
yeah, so what we do is literally this oil, you squeeze it in a container and then you can monetize it. You can recover the oil and reuse it. That's the beauty of this approach, that you don't throw it away, it doesn't become landfill, but actually you can use it. So we can use it 20, 30 times, squeeze it, use it. And then of course, what's the natural question? After 30 cycle, what happens? What do you think, Kasim?
Can it
what
be
happens to
refined?
household sponge? Household sponge, after we use many times, what happens? It starts to break, right? And into pieces. But remarkably, the same, we can take the sponge and combust it to form carbon. So it has carbon plus some iron oxide based compounds. They become an amazing anode for a lithium ion battery. But imagine, so you have 30 times we use it, get all the oil or get all the fossil fuel cleaned up, and then it starts to break apart. But that sucker is so committed to environment. It says, okay, burn me, make me a carbon, and then iron oxide acts as a lithium ion battery anode. It's called conversion reaction. And so you get very high capacity and you can use this now as an anode. So this is called circular economy. That's really in vogue in recent years now. So in material science, one of the biggest problem among others is sustainability of materials, correct? Especially rare earths, you know, these are 99% of that is owned by Chinese. And all those were actually 100 years ago, we had 90% of world supply. But now all our commercial interests have gone wayside. And so Chinese are owning a lot of the mining companies. Anyhow, so that sort of explained the circular economy. So now the question is, how does the functionality of OHM Sponge, why and how it happens? And this is where I'll spend next few minutes and describe to you this facilities which are available to all of you at Northwestern as a part of our core facility concept. And we call it Nuance Center and Shine Resource. So you get a red carpet welcome here. Can you see the slide? Yeah, good. So we think it's not just for me or us, it's a resource for the whole region. In fact, we are part of a national center of excellence in facilities. So it's not limited only to Northwestern, it's the whole country. And it's, you know, a lot of the capabilities, a lot of details. So I don't want to bore you with many detail, but give you some conceptual ideas as to why and how we do this. Okay. And part of the reason this has happened is, you know, when your parents went to school like Northwestern, they went largely for knowledge. Because if you might remember that people say that, you know, you go to Northwestern, MIT, because those are fountainhead of knowledge. Those are the institutions. And knowledge is important, but now it's ubiquitous. A kid in a cell phone in Kinshasa has the same access to knowledge that you do at Northwestern. So why do you become a Northwestern graduate is because now the paradigm has shifted to go from knowledge to analysis, synthesis, creativity, higher level of learning. So at Northwestern, it's not just about knowledge, but what you do with the knowledge, how you analyze it and synthesize it. So there's a remarkable shift that's happening in higher education in the last 2 decades, where there's a tremendous emphasis on engagement. It's no longer just about research and write papers, but how do you know, connect with the region, nation, global? How do you couple not just scholarship, but education, industry relationship? And a lot of these capabilities are extremely expensive. If you remember, the genome analysis was done with $1 billion in the past, 20 years ago, and now you can do it in less than a few $1,000s. And so that shift is just very palpable. So the university's role is no longer just about scholarship, but it's also about economic engine. And so you can imagine in the past, you know, it was all about students and papers, but now it's not just students, but students were trained in other fields like communication, finance, accounting, problem solving. It's not just about papers, but we write patterns, we have intellectual property, innovate. And last but not least, I think modern universities like ours offer this amazing resource of facilities, instrumentation, and that's what we do at Nuance and Shine. So Nuance is a collection of capabilities that are accessible to all our users and collaborators. So there are many legs of Nuance. So Nuance stands for Northwestern University Atomic and Nanoscale Characterization Experimental Center. That's Nuance, and this is what I meant, that there's going to be a quiz, all the acronyms you need to spell out. So it's an overarching idea, and within that you have EPIC is an electron microscope. So if you need to use electron microscope, you come to EPIC. We have all of these fantastic things that some of you may know, SEM, TM, etc. Then on the other side, NuFab is our fabrication facility, silicon and others, so to be able to do lithography, patterning. Those are the capabilities for NuFab. And in between, you have BioCryo. We felt strongly that's, you know that 2017 Nobel Prize went to cryo-EM. And those innovations are very specialized. So we felt strongly that BioCryo is a separate unit where you look at soft, hard interfaces like biology, physical science, drug delivery, or biofilm formation on implants. So there are all sorts of problems which on one side is soft, fluctuating, is determined by KT termed in the thermodynamic. On the other side is a hard ceramic or a metal. It's robust mechanically. So it's a very intellectually challenging problem how to analyze the interface. And that's what we do with Nuance BioCryo, for example. KEC2 is a surface science. So many times you need to know what my surface is made of compositionally, structurally, bonding-wise. Like take carbon, for example. Carbon, if it is amorphous carbon, it's such a useless material, not particularly exciting. But a tetrahedral carbon is diamond. So the same element is going to give you the same composition, carbon. But clearly diamond is very different than amorphous carbon. And that comes from spectroscopy. And that's what we do, for example, in KEC2. Speed is our scanning probe, just the way you can imagine how blind people read. They use finger and use the ups and downs of the surface as a way of recognition, right? So it's a very similar concept. Let's just imagine instead of your fingertip, you have a nanoscale tip. And then you can, look at the bumps and bruises on the surface at the level of molecules. So if you have molecules, DNA on the surface, you can, it goes up and down, and that height of the DNA you can measure. And so we have some freshman students who do research in Nuance Center on this capability. So they're run by technical staff, so you get trained, assistance, collaboration, and this is an asset for you when you arrive at Northwestern, for example. So over the years, we have grown. This is an administrative slide. You're not going to be that excited. And then the next stage is collection of a lot of the facilities like Nuance forms Shine. So Shine is an NSF-supported center at Northwestern that I run with Andrew Cleland of U Chicago. And as you can see here, is soft and hybrid nanotechnology. That's what we do. Soft means, many times we use cheese, ice cream, and some of those materials are materials. And Kraft food, which is a next door neighbor to us, they use our facilities. So I often say there are not many places in the world where you actually do an experiment and then you eat it. And you tell me which other universities can boast that. So at Nuance and Shine, we can do that because the soft materials are all kinds, like chewing gum. So we have programmed with Mars to understand those flavor bursts. So it turns out there are tiny capsules that have flavors in it, and you can actually mimic that in an SEM, a chewing action, and watch what and how things go. So there are all sorts of interesting form function problem and material science that we can use using our facilities. So it's an intellectually very exciting area, soft hard interface. As you can see some example, on one hand you have DNA or proteins and those kinds of soft material. On the other hand, you have semiconductors, hard material, and there's a life in between, and at the interface between that, you might have heard John Rogers and his bioelectronics. You have a hard electronics stuck to human skin. So that's a very classic soft hard problem. So there are many such challenges at the interface surfaces that require capabilities that we have at all the units that you see at the bottom: Nuance, Shine, Merced, Northwestern. So Shine is simply a coordinated effort of facilities that you see here. Nuance. IMSERC is a molecular nanotechnology, which the faculty director is Fraser Stoddard, who won the Nobel Prize a couple of years ago in chemistry. As a result, he has invested a lot in molecular nanotechnology of IMSERC. NuFab, I already talked about our fabrication. Cohen facility. NUCAPT is a unique atom probe tomography facility that's run by Seidman and Dieter Ischheim. This is one of the rare world-class capability to look at atomic scale structure chemistry using so-called local electrode atom probe type of measurement. SQI is run by Sam Stoop, and John Rogers is a part of that. It is meant for regenerative medicine, soft hard interface, a lot of bioelectronics, flexible electronics. So you can see that we serve many different communities in this sort of a broad rubric of soft and hybrid structures. And so I wanted to end by emphasizing what's so special about Northwestern. I often show this slide really to hone in the point that if I hear, I forget, I see, I remember. When I actually do, I understand. So even at the freshman undergraduate level, we emphasize hands-on training and hands-on experience for our students so they understand how to do things better. And so we're very excited that a lot of our course curricula are integrated with Nuance and Shine so that you get not only classroom exposure, but you also get hands-on exposure. And this is to emphasize the point that I meant. The pyramid is no longer just about knowledge, but how you do with it, and ability to do group projects. You learn to get along with others, take a problem and go deep dive into it using combination of theory experiment is what students often do. We work with locally engaged with museums such as Art Institute, Film Museum. So there's a lot of outreach opportunities for those of you who want to make a difference in, you know what's going on in the world, in America in particular, the last few weeks. these are the types of opportunities we need to leverage. You know, so museums are very neutral, politically neutral entities, at least so far. We'll see if that is the case. And so, you know, engaging students with museum activities is always very exciting. So these are some examples of analysis of paints and other work of art. And often the case, you know, artists become famous after they die. So then you start to find out what's so special about the colors and pastels. There's a lot of emphasis in recent years for looking at how phenomena occur dynamically. So it's not just about analyzing OHM sponge, but how does OHM sponge function as it functions? So we have so-called environmental SEM, where we can actually mimic an oil absorption experiment in situ, and then try to understand why and how these things happen. And so there are a lot of such capabilities at Nuance. And most recently, we moved into a brand new building, where I'm actually sitting, where a lot of our instruments and capabilities have moved for the first time integrated way. So we were scattered for the last 20 years in many different parts of the university, and now we have much of our capabilities are now collected in one or two floors in AB. So that offers a great opportunity for a student that they have multiple instrument access, but also technical staff. What you see here are the series of staff offices. So if one is on vacation, you still have many others you can engage, which wasn't the case before because this was all spread out. So that's where I thought I would end by saying that one last initiative is extraterrestrial. So some of you who are space buff might have followed Hayabusa 2 as a mission by Japanese space agency to go to an asteroid, land, collect the material, and bring it to Earth. So this year or next year, they're going to bring back asteroid material, and then there's opportunity to understand. So by one theory, life on Earth might have started through an asteroid or a comet bringing carbon. And so there are some really profound issues that we might have answers to by analyzing extraterrestrial material. This is a part of the report. I was part of a committee for National Academies and NASA last year, and we came up with this report, and we like to believe that Nuance has a competitive advantage when the solicitation comes. After post-COVID, there will be some missions to bring back material from extraterrestrial sources like asteroid, comets, and that's the next stage for Nuance and Shine resource.